Welcome to our presentation on SADIR, Shape-Aware Diffusion Models for 3D Image Reconstruction. I'm Nivetha Jayakumar from the University of Virginia. The reconstruction of 3D volumes of real-world images from a sparse stack of 2D slices has been a long-standing problem in computer vision, and in medical imaging in particular. Applications of this type of reconstruction include the reconstruction of 3D brain MRIs from sparse 2D frames and the reconstruction of the shape of the myocardium given the 2D slices. These sparse stacks represent the way in which medical scans for these organs exist in the current clinical setting. And the reconstructed 3D volumes help clinicians make precise disease diagnosis, prognosis, and formulate better treatment plans. The current state of the art deep generative model for image synthesis and reconstruction is the diffusion model. However, the existing generative diffusion models do not consider the shape of the object during reconstruction, resulting in artifacts such as discontinuities, holes, and joint appendages, which should not be a part of the original object. Hence, we propose a shape-based deep reconstruction framework with the goal of effectively utilizing the geometric shape features available in the limited number of sparse 2D slices of an image to perform 3D volumetric reconstruction. Here's the outline of our talk. Moving on to the background on deformable shapes and atlas building. Deformable shape representations reflect the expansion and shrinkage of geometric features in images and are robust to change in texture and intensity. As we can see here, an object, here the brain ventricle, can be deformed from one representation, that is the source, to another, which is the target, using geodesics, which are shortest paths of deformations. In our framework, we use the atlas or mean image as the deformable shape representation, where it is obtained as a result of the atlas building process via Fréchet mean of a group of images. The images in a group can be represented as deformed versions of this template image. The goal of the atlas building framework is to minimize the energy function given here, which is a sum of the dissimilarity term based on a distance function between the deformed template and the individual image, and a regularization term obtained from the LEDMM algorithm. Moving on to our method, shape-aware diffusion model for 3D image reconstruction, that is SADIR. Our framework consists of two separate networks, the atlas building network parametrized by theta A and the reconstruction network parametrized by theta R. The atlas building network follows the atlas building framework mentioned earlier, but uses an encoder-decoder model to predict the deformation fields and update the atlas. The loss function of this network is the same as the atlas building framework's energy function. The reconstruction framework consists of the diffusion model with the forward diffusion process shown here, where the input image's image signal is slowly distorted over time by adding small amounts of smooth Gaussian noise. And the forward process can be parameterized using this probabilistic equation given here. While in the reverse process, we aim to reconstruct the ground truth image. Before beginning with the reverse process, we concatenate the stack of sparse 2D slices, followed by the atlas from the atlas building network to form a 3-channel input to the reverse diffusion network. The reverse process consists of an attention unit parameterized using excitation layers and time embeddings, which is used in a single-step prediction of the initial momentum field, which is used to obtain the deformation field using the geodesic shooting algorithm that we saw earlier. That is then used to deform the atlas to obtain the reconstructed 3D volume pertaining to the input 2D sparse slices that are concatenated during the reverse process. The loss of the reconstruction framework is given here, which is the L2 norm of the ground truth and the predicted 3D volume, followed by a regularization metric. In the case of shape-based reconstruction of binary label maps, we add an additional weighted dice loss, which helps reconstruct the shape better. Here's the complete architecture of our framework. Moving on to experiments. We evaluated the performance of our model on 3 different datasets. 3D brain ventricles obtained as binary label maps from the OASIS dataset, 3D myocardium volumes obtained by processing mesh data available on MedShapeNet as binary label maps, and 3D brain MRI volumes obtained from the OASIS data repository. All datasets were downscaled to a resolution of 64 cube to reduce the computation complexity. The sparse stack of 2D slices were obtained by sampling 8 slices at fixed indices from the 3D volumes. We then compared our framework to 3 state-of-the-art networks. The 3D unit, though effective in reconstructing the volume, aggravated artifacts seen in one slice across multiple frames. The traditional denoising diffusion probabilistic model has several holes and discontinuities along with joint left and right ventricles. This model does not preserve the shape of the organ. DISPER, which is a recent work where they perform reconstruction using a topological laws along with the DDPM, effectively reconstructs the left and right ventricles without discontinuities. However, it still has joint appendages and does not preserve the shape of the tail of the ventricles. But our framework SADIR preserves the shape of the ventricles from anterior to posterior along with high performance metrics. And the snapshot of our predictions as compared to the 3 SOTA models is given here. So here are the results of validating our method on the 3D myocardium volumes along with SOTA model comparisons. Here you can see that the 3D unit constructs parts of the myocardium that are not a part of the original organ, while the denoising diffusion probabilistic model is unable to reconstruct the missing frames without discontinuities. Though DISPER preserves the shape of the organ, it does not have a smooth surface, particularly in regions where the 2D slice cannot provide information regarding the thickness of the organ's tissues, such as the opening of the myocardium. Our method preserves the topological features of the organ. So here's a snapshot of the predictions of SADIR along with the predictions from other SOTA models. So given here are the performance metrics for all 4 aforementioned models on both the datasets. From here, we can see that SADIR outperforms other models with high dissimilarity coefficients and checkered similarity scores with minimum standard deviation. The same pattern is observed for the 3D myocardia as well, where we have high dice, checkered scores, and low robust Hausdorff distances for SADIR. So here are the qualitative results from evaluating SADIR on 3D brain MRIs. We have compared our model to that of the denoising diffusion probabilistic model, and we can see that the DDPM fails to reconstruct brain volumes with the right shape of different parts of the brain, such as the ventricles, the sulci, and gyri. Though there are errors in the shape of the sulci, SADIR reconstructs the complete 3D brain MRI from 2D slices with minimum normalized absolute error, as seen in the plotted error maps. So to conclude, we have developed a shape-aware diffusion model to reconstruct 3D images from stacks of sparse 2D slices. We did this by introducing shape features to preserve topological structures of the objects present in the volume. Future work includes uncertainty quantification from the probabilistic process, and the code is publicized and the link can be found here. Thank you.